Okay, so in spherical, you're going to have three variables, rho, theta, phi. And what we're going to do now is look at how you can describe the solids G using these variables. And yeah, so anyway, I'm going to try to draw this. So think of concentric spheres. That's pretty much what we're going to talk about. So let's say we have a sphere, two spheres, one that intersects right here, one that intersects a little higher than that. And let's say I draw well, I'm not going to draw the actual sphere. I'm just drawing the portion that I need.
It's right there. It's right there. No, did you see it?
Oh, the small little ball right there?
Yeah. Wait, what?
You'll see.
Oh, okay. Waiting. Is it like pieces cut out of the sphere?
Yes.
Two angles?
I'm just trying to get things lined up here.
Yeah, I think we should have an object.
Okay, so here's what's going on.
That was actually pretty good.
Here's that polar region R. Okay, and our two angles are right here, just like they were yesterday for cylindrical, theta 1 and then theta 2. But now we need these other two variables, rho and phi, right? Well, rho is just the radius of the sphere. So from here to here, let's say that's rho 1. And then from here to here, let's say that that's rho 2. Okay, so there's two out of the three variables. And now if you recall what phi is the angle with respect to the positive z-axis, right? So if I go ahead and draw two of those, so let's say that this is phi 1, and then let's just say this is phi 2 here.
Is it going to the same wedge?
Yeah, we're going to get a new wedge here that's trapped between the two spheres. And they're going to look something like this.
Oh, okay.
Oh, didn't work out as well as I would hoped, but anyway, there is a little volume here trapped between the two spheres, between these two angles.
Wait, is rho on?
Rho is the radius of the sphere.
Oh, so it doesn't matter.
Doesn't matter where I put it, yeah. But I'm not going to even attempt to put it here, because it's just going to overcomplicate it. Yes?
Does that extend like from the XY plane or from like the Z axis?
From the z-axis. So from the z-axis down to wherever we need to get to. Okay? That's not a bad version. Here's probably a little bit better one.
Wow.
So is that like from the Z just another wedge that was pulled out? Like if I take that out, there'd be like a gap in there?
Yes. So again, here's the region R, and you guys kind of see the portion of the sphere here? If you follow that up, and then you range phi from phi 1 to phi 2, then you get this little volume in here, this little spherical wedge. Okay, so that's what we're talking about here. Let me... Okay, so then inside of this wedge, we have coordinates, rho sub k star, theta sub k star, and phi sub k star. The triple integral is going to be defined as the limit as n goes to infinity of the volume of these little wedges, which we're going to call delta v sub k. And obviously we're just going to evaluate the function. Again, it's not a height anymore, it's something else, but f of rho sub k star, theta sub k star, phi sub k star. Oops. Okay. So look, we're going to skip the derivation for what this turns into, mostly because it's long and I can prove it to you in 14.7 using a different method, which is a lot shorter. So here's what you need to take from this. The triple integral in spherical coordinates rho, theta, phi, dv is going to be equal to the triple integral, and we'll use bounds. We'll just do the same ones that I set up in there. So we'll go rho is from rho 1 to rho 2. Theta is, let's see, actually let's go phi next. Phi will be from phi 1 to phi 2. Theta will be from theta 1 to theta 2. And now the dv, here's the very important part. In cylindrical and in polar, what was the extra factor that popped up in the integral? The r. Okay, in spherical, it's going to be rho squared sine phi. That's the extra factor. That's sort of our adjustment or scaling factor when we do switch from rectangular to spherical. And then we, of course, have our d rho, d phi, d theta.
That was the easiest way to go.
Yes. A lot of times, some of those really complicated integrals, and I'll show you one in a minute.
It's long.
Yeah, I mean, it's just way longer, but if you do it in spherical, much shorter. The problem is, again, the setup. Okay, so if we can get good at setting these things up, then life will be easy. All right, so here's an example. And again, for now, don't worry about, we all know where that r came from earlier. This rho squared sine phi, for now, just kind of trust it. I'll show you where it comes from in 14.7. All right, so let's say you wanted to find the volume of the ice cream cone. Bless you, yes. Bounded by, of course, everybody eats ice cream. By x squared plus y squared plus z squared equals z. And z equals the square root of x squared plus y squared. Okay. So, again, probably a good idea to sketch what's going on, even if it's not the best drawings, just enough that you can kind of see what's going on. This is going to be a sphere, right? If you're not sure where, you could complete the square. It'd be x squared plus y squared plus c squared. We're going to subtract z. To complete the square, I would add a 1/4, right? So then we get x squared plus y squared plus z squared. Nope, not anymore. Z minus half equals 1/4. Thank you. So the radius of the sphere is a half. The center is at 0, 0, 1 half. So essentially, I have this sphere of diameter 1. You guys kind of see that? Eddie?
Why isn't there like 1/2 anywhere in there?
It is. It's right here.
Oh, I see.
The center has been shifted up a half unit. The whole diameter would be 1, so that the z-intercepts are 0 and then 1.
I didn't know the whole diameter's wrong.
Because the radius of the sphere is a half.
Half squares. I got you.
Okay. So there's the sphere. What's this going to be? Some cone, right? Some cone. And now, we're not going to draw the whole thing, but more importantly, it's what do we get with the cone when we intersect it with this sphere? An ice cream cone, yes. You get a little circle here. And there's the ice cream cone. Do you guys kind of see it? So there's the cone part, and then up here would be the ice cream, I guess. Okay, so we're trying to find the volume of that.
The little circle. The purple thing.
Well, this is kind of here.
The whole cone.
The whole cone, well, no, because we can't find the volume of the whole cone. It's the cone from here to the circle, and then the volume of the circle up to the sphere.
So the whole cone. Or like the whole ice cream.
Yes, the whole ice cream cone.
Okay.
Yes.
Wait.
Cone and ice cream included. Yes.
Oh, okay. I got it.
It's the everything inside of the cone that's inside of the sphere. Right?
Yes.
Okay.
Inside of the cone, inside of the sphere. Absolutely. All right. Are we good?
Yeah.
So,
I don't really see why you shaded that one.
because we need to know what kind of intersection this is, right?
Ah.
Because when we do the bounds in region R, we need to know what projection that is onto the xy plane.
Nice. Okay.
All right. So let's find the bounds. So if we're finding volume, then we just do 1 dV, or in spherical, that would just be 1 times rho squared sine phi d rho d phi d theta. So now we need to figure out what rho is. Well, what is it?
Oh. Oh.
So think about like in polar, you know how we started at the pole and we went outward to figure out what curves we intersected that with? Think going out and what we run into. So if these are the boundaries, so just take any point in here and go out, what surface do you run into? The sphere. So we're going to go from 0 to the equation of the sphere in spherical coordinates. Okay, now if you know a little bit about polar, you guys remember the whole thing about like how cosine was a circle on the right side? While in spherical, a cosine is a spherical on the top. If you don't buy that,
That's like the complete opposite.
if you don't buy that, here's how we can figure it out. What's x squared plus y squared plus z squared? Rho squared. Z is rho cosine phi.
Oh, and then you divide the.
And then if you simplify, divide by rho, rho is going to just be cosine phi. So we're going from 0 to cosine phi. So that's the boundaries for rho. Phi So imagine we're starting right here. Okay. If we start here, what does phi equal? 0. And then we range phi a certain angle until we get this intersection right here. I don't know what that's going to be, so let's find it. So for phi, if we set these two equations equal to each other in spherical, that's probably a good way to go. So we know that z equals, well, or better yet, I guess we can just use this equation here. Z is rho cosine phi. If we plug in the equations for x and for y, that's going to tell us on this cone exactly what this angle is because, well, that's what we need to find. The cone is what is restricting this phi from going all the way down any further. Okay, so
Doesn't the phi go up?
what's that?
Doesn't the phi go up?
It starts here and it goes down.
It does?
Yes.
It doesn't go from down and up?
No, never. Never did, never will. So if we plug in the conversions for x, let's see, x was rho sine phi cosine theta. So that'll be rho squared sine squared phi cosine squared theta. And then y was rho and then sine sine, so it'll be rho squared sine squared phi sine squared theta. And if we simplify, let's see. Looks like I can factor out a rho sine squared phi, which gives me cosine squared plus sine squared. Well, that's nice.
Oh, wow. That is nice.
So this is just rho cosine phi equals rho sine phi. In other words, cosine phi has to equal sine phi. You don't even have to go any further. What's the only angle where the cosines and sines are the same?
5/4.
So going back to the bounds, rho is from 0 to pi over 4. And now theta, remember, now we're looking here. If we have a circle on the xy plane, that's the shadow, right? Theta is going to be from 0 to 2 pi. So there's the setup. And now to calculate the integral,
But I don't.
Usually the 2 pi.
because remember theta starts here, and in order to cover the entire circle, we'd have to go all the way around.
Wait, so for the. Yeah,
How we got phi?
Or like, what is it?
right.
Phi, in general, so let's say this is x, this is y, and this is z, right? Let's say we have a point. Let's go a little further out, sorry. So let's say we have a point sitting out here, right? Then phi is going to be the angle here. Positive z, and then wherever the point is in 3 dimensions.
It goes out to the, like, outside of the circle, of the sphere.
Well, it can. It's just a constant line that goes. So, I mean, you could say that phi is right.
So phi happens when the sphere intersects the cone, is that what you did?
Yeah, because, I mean, here's where phi starts, right? We start here on the positive z-axis, and in order to get to the intersection here, we're ranging phi from 0. So we start on the line, and then we're going this far out. So there's phi right here.
That makes sense. So you made the equations equal to each other and solved it from there?
Well, I didn't even need to because the equation for the cone was z equals x squared plus y squared. So if I just plug in the spherical coordinates into the cone equation, that tells me what phi has to be. Phi is a constant. Yeah, in fact, for cones, phi is always. I mean, that's the way to convert it. Remember, like if I told you that phi was, let's say, oh yeah. let's say phi was, I don't know, pi over 6. Okay? If phi is pi over 6, that means that from this z-axis here, we're going to rotate or come away from there how much? 30 degrees, but everywhere, right? So 30 degrees here, 30 degrees there, 30 degrees there, 30 degrees there. And essentially what happens is when you connect these, you get a cone.
No matter how far we go?
Yeah.
Oh.
Does that make sense?
It does make sense.
Okay. In this particular case, because of the way the cone was defined, it's just pi over 4, because when you plug in the spherical equations for x and y and z, there's your cone. Okay? All right, so let's finish the problem. The calculation is actually not hard. 0 to 2 pi, 0 to pi over 4. The first round of integration makes rho squared into a 1/3 rho cubed. We still have sine phi, but now we're plugging in rho is 0 to rho is cosine theta. Oh, yep, it is cosine phi. Thank you. That was my bad. And when you do that, you get 1/3 cosine cubed phi sine phi. Rho equals 0 doesn't do anything. Oh, forgot my d phi d theta. D phi d theta.
And then it's a U substitution.
Yeah, because now you can do u is cosine, right? So that's going to become, let's see, the derivative of cosine is sine minus sine, so we need a negative. The third goes to 4, which means we need a 1/4 times the 1/3, so negative 1/12. Cosine goes up to 4, and then we're good. So now phi is from 0 to pi over 4. Plug in the bounds. Cosine of pi over 4 is root 2 over 2. So just 1/4
But then times negative 1/12.
times negative 1/12.
148.
You sure?
Yeah.
Don't make me question it. 2 over 4.
What's that for the question? Times negative 1/12.
No,
1/4.
I'm leaving that on the outside.
Okay.
No, that's way too much.
No, I know.
Okay. So we're saying negative 1/4 or negative 1/48.
Yeah.
Because
Negative 3/4
Plus 1/12.
Negative 3/4.
oh, and one person.
And then we subtract.
And you-
Wait. Shouldn't it be
No, because
Three.
you hold that you
48?
Yeah, he's adding 12.
He hasn't done it. He's adding the 4.
I'm adding in. Now we plug in 0.
Carry on,
Okay.
carry on.
Now we plug in 0. So we're going to add in what? 1/12,
Which is 3/48.
which is 1/16, right? Bless you. So 1/16 becomes 1/16 theta from 0 to 2 pi. So final answer is pi over 8. Okay. All right, let's do one more spherical. So you got to get the hang of setting these up, but also the hang of, and this is probably the more practical.
Memorizing the original.
Yeah.
Koji, how did you go from?
That's the deal.
How did you get from negative 148 plus 1/2 to
1/12.
That was 1/12.
3 over 48
What is it?
plus 4 over 48 is 1/16.
Oh.
Okay. So the last thing is converting. I mean, this is really where these equations come in handy. So let's say we have a triple integral over a solid B of e to the x squared plus y squared plus z squared to the 3/2 dz dy dx, where B is the unit ball. Unit ball meaning x squared plus y squared plus z squared equals. Mhm.
It's funny that we're calling it ball.
Unit sphere, sure. I like ball better.
I like it too.
Now, setting this up in rectangular, not advised. I mean, you can see what's going to happen, right? You'd have to get z alone in the equation x squared plus y squared plus z squared equals 1. You got all these nasty roots in there. We don't want to do that. So let's try spherical. E to the, what's x squared plus y squared plus z squared in spherical?
The P squared.
Rho squared, and then that's to the 3/2. It'll become just, yeah. We want rho squared sine phi d rho d phi d theta. In a unit sphere, rho ranges from what to what? 0.
2 pi.
Rho is the radius of the.
Right.
So 0 to 1.
0 to 1. Right.
Rho is just the radius of the sphere, right? So, yeah, don't think angles yet. So all we're talking about is the sphere, right? So if we start at the origin, rho is 0. If we go outward, we run into the equation of the rho equals 1, which is the unit sphere, okay? Phi. Phi starts up here, so 0 to,
2 pi. 2 pi.
careful, it's just pi.
Why?
Because from 0 to pi will cover the entire sphere. Because when you do theta, theta is the one that wraps around, right?
What?
We did the call because it like has that intersection.
Someone
Wait,
need,
what if you do 0 to 2 pi and then theta 0 to pi?
by definition, phi cannot be any larger than pi.
Okay.
When we first talked about these,
Oh, they had it.
so this is the highest, this is the lowest and highest value for phi.
Gotcha.
Theta, there's where you're thinking 0 to 2 pi, right? Because it goes all the way around.
Thought it was on something.
So this is how to convert it. And now as far as evaluating it goes, let's see, not too bad. 0 to 2 pi, 0 to pi, 0 to 1. We said this was e to the rho cubed, right? So if I focus here and let maybe u equal rho cubed, I get the 1/3. Does that make sense? Pull out a 1/3. So 0 to 2 pi, 0 to pi.
Use substitution, right?
Yeah.
Nice.
So then we get e to the rho cubed sine phi evaluated from rho equals 0 to 1 d phi d theta. So 1/3, 0 to 2 pi, 0 to pi. Plug in rho equals 1. We just get e sine phi minus sine phi. Do not make the mistake of seeing a 0 here and saying, oh, that goes away. Especially when there's e's in there. Okay?
Nice.
So let's see. Derivative with respect to phi of sine is going to be negative e cosine phi. Derivative of, or integral of sine is going to become positive cosine. Phi is from 0 to pi. Plug in the bounds. At pi, cosine is negative 1, so we just get e minus 1 minus, plug in 0. Cosine of 0 is 1, so that's just going to be negative e plus 1. It is, but it's not hard. Let's see. This is just going to be 2e.
So why is it e minus 1? Should be e. No, it is minus 1.
Minus 2. D theta. This is a constant. So I'm going to have 2e minus 2 times theta. Oh, drop the 1/3. Don't forget the 1/3. From 0 to 2 pi. So the final answer, I could pull out a 2 if I wanted to and make it 4 pi over 3 e minus 1. Okay.